All right, friends, welcome back. So we are live right now. All right. So it's great to see you back again. So first thing first, I wish you a very happy and a prosperous Diwali. आप सभी को मैं हार्दिक दिवाली के शुभकामनाएं. All right. So very happy Diwali to all of you. और आज हम वेक्टर अलजेब्रा में डिस्कस करेंगे वेक्टर ट्रिपल प्रोडक्ट्स के बारे में, राइट? तो अगर आप लास्ट प्रीवियस कुछ लेक्चर्स जब देख रहे होंगे, राइट, तो उस लेक्चर्स में मैंने ऑलरेडी बेसिक्स ऑफ वेक्टर अलजेब्रा डिस्कस किया है और उसके साथ साथ हमने प्रोडक्ट ऑफ वेक्टर्स के बारे में भी डिस्कस किया, राइट? एंड देन वी स्टार्टेड टू डिस्कस अबाउट व्हाट इफ वी टेक प्रोडक्ट ऑफ थ्री वेक्टर्स, राइट? और वहां से हम चालू किए थे जहाँ पे हमने सीखा कि हाउ वी डू द स्केलर टेलर प्रोडक्ट और हाउ द स्केलर टेलर प्रोडक्ट थिंग इज डिफाइंड. So today in this class we will discuss about vector tailor product, and that will be the motto for the entire chapter today. Alright, so let's start. So this was a result which we finished up in our previous discussion about the volume of the tetrahedron, and we will definitely solve some questions in the upcoming part of the lecture, but for the time being let's first go on to understand the vector tailor product things. Alright, so let's start. Vector tailor product can be so if I talk about vector tailor product result, now why do we perform this product? There are reasons to it, but let's first understand that what is this vector tailor product signifies, right? So when we perform the product of two vectors, we have seen that the product of two vectors can be performed in two different ways. One which gives a scalar result and one which gives a vector result. Similarly, for product of three vectors taken at a time, we can also have two different results. One which give again a scalar result and which we have already discussed, that is basically the scalar triple product. And that scalar triple product was basically giving you the result for the volume of the parallel pipe. So the volume of the parallel pipe was a 3D figure, and we saw how that scalar triple product is basically geometrically interpreting that particular volume. So that's what we have discussed. So in today's session, we are going to discuss about another important product which is basically called as the vector triple product. So let's try to first define what this particular product looks like. So let's try to do the definition of this product. So if I talk about three vectors, let us say I take three vectors, A vector, B vector and C vectors are my any three vectors I have with me. Then if I perform this result, then the vector tailor product is defined as cross of A cross B cross C. Now this position of this bracket plays a very significant role. Okay, so this particular way of defining a product of three vectors is nothing but it is called as the vector tailor product, or maybe I can do the product as A cross B first, and then cross with C. So this kind of product is called as vector triple product. Is called as vector triple product. Alright, so this kind of product is called as vector triple product. So let's first understand and how do we calculate it and what's the theorem behind that. So generally, and the result is already defined as, so if I do A cross B cross C, let us say I put a bracket over here, then the result is very simple. The way to remember it is basically, so you have A cross B cross with a bracket over here. So wherever the bracket is put, that will come over here as B vector and C vector. And you take the farthest point and take a dot product with it. So A dot C over here, and then minus, you take the nearest point, and that is A dot B. So if you calculate this particular expression of the vector expression, you will get what is the result for the vector triple product. I hope this is clear to all of you. Alright, so this is how we calculate the results for vector triple product. Alright, so this is how it is defined. Okay, so this is a theorem on how a vector triple product is defined. I hope the way I denoted the result, it will be very easy to remember, right? Now let's try to see that how this particular result come into being. That is, let us try to talk about the proof of this particular result. Let us say, first of all, in order to look at the proof of this result, let us first of all assume that I have an unknown vector R which is defined as by this vector triple product. Now I said that the result of this vector triple product is basically going to be a vector. So let's assume the R vector is the result of this vector triple product. Now, what you observe over here is that you see it is a cross product. So if I consider this as another vector, and this as the A vector, so I can see that it is just a cross product of two different vectors. I can say like that, right? Now if I have this result that it is basically given as A cross B cross C, so B cross C can be assumed to be another vector and A vector is present as it is, so it is just a cross product of two vectors. So since it is a cross product, we have already seen that whenever we perform a cross product, the result is perpendicular to the individual vectors, right? So therefore, I can say that my R vector is going to be perpendicular to A vector and my R vector will be perpendicular to this particular vector as well, that is B cross C vector. So the R vector will be perpendicular to both these vectors. I hope this is clear, right? Now, if I have this result which is perpendicular to R vector is perpendicular to A vector and B cross C vector, also what I can talk about physically. So if you try to assume this particular scenario geometrically, so let's try to understand what does this geometrically mean. Okay, so let's first me draw the x, y and z axis so as to give you a better understanding. So let's say this is my x, this is my y and this is my z axis, right? Now if I say that this b, so if I say that my b and c vector are lying in the xy plane, so when I do a cross with b cross c vector, so this particular vector, that r vector, so this particular vector is obviously perpendicular to, so b cross c, this particular vector, if I call this as d vector, so this particular vector is perpendicular to b vector and it is also perpendicular to c vector, right? So this d vector is perpendicular to b vector and c vector as well, right? So from here what I can conclude saying that, now please try to imagine this situation in the three-dimensional plane. So if I say that if I have a plane something like this and I have b vector over here and c vector over here, so when I perform the cross product, I am going to obtain a vector which is something like this. Let us say it is out of plane and this n cap denotes the direction, or let me directly write, this is my b cross c vectors which is out of plane and perpendicular to both these vectors, right? And it is out of plane. So if my r vector is also perpendicular to this vector, then my r vector must definitely lie somewhere over here, right? So my r vector should also lie in this plane. So r vector should also lie in this plane in order to be the r vector to be perpendicular to b cross c vector, because my b cross c vector is this particular vector and my r vector is this, and if it is lying in the same plane as b and c vector, then only it is going to be perpendicular to this b cross c vector, or which is a d vector, right? So therefore what I can conclude over here is that r lies in the plane of r lies in the plane of b vector and b vector and c vector. So from here what I can say that the result, that means my r vector result, is definitely going to lie in the plane of b and c vector, right? So from this result what I can understand that, now I have already seen and we have discussed that whenever these three vectors are lying in the same plane, that means these vectors are coplanar vectors, and we have seen by the basics of vector algebra that if three vectors are coplanar vectors, then one of the vector can be written as a linear combination of two vectors. right? So from here, I can represent my R vector as some linear combination of lambda times B vector and let us say some mu times C vector. So I can represent this R vector as a linear combination, right? So, alright. So this is basically given as a linear combination of B and C vector, right? Now, once I know this particular result, then from here, what I can say is that, so if I have this result as follows of my R vector, now also I have this result, that is my R vector is perpendicular to the A vector as well. Now we have seen by basics of scalar product or dot product, we have seen that whenever two vectors are perpendicular, their dot product is definitely equals to 0. So this is a simplified result, right? So if I apply the same result on this particular vector, so let's apply this particular result, then I can write lambda times of B vector plus mu times of C vector. And if I take a dot with A vector and equal it to 0, then the result is going to be, so from here I can obtain the result. From here, I can obtain the result, that is lambda times B dot A plus mu times C dot A. So I can obtain this particular result, that is lambda times B dot A plus mu times C dot A, right? Now from here, I can get a relation in X and Y saying that lambda by A dot C vector is equals to minus of, or yeah, minus of mu times B dot A is equals to, let us say another constant, let us say some constant zeta. Let us say this particular constant zeta. So this is a ratio, which is an identity ratio, right? Which is equal to some constant value. Let us say that zeta. Okay. So if it is constant, so from here I can find my value of lambda to be A vector dot C vector times that constant zeta, and similarly my value of mu can be obtained as minus zeta times B dot A vector. So it is a dot product, right? Just a dot product. Okay, so I have obtained my relation of, so I have just reduced the given vector relation of two variables to one variable zeta. Now if I solve for zeta by just substituting back into this following equation, so from here I can write R as zeta times of A dot C with B vector minus of B dot A vector times C vector, like this. Then just to find out the value of zeta, then zeta will be a arbitrary constant. So R vector is definitely going to lie in this particular direction, right? So in this particular direction, whereas my zeta is just a constant magnitude. Now in order to find out this value of the zeta, what I'm going to do over here, it is very simplified. So if I substitute the value of lambda and mu over here in the following relation of zeta, and then since we can apply, so this particular R vector is given as A vector cross B cross C, right? This was what is defined as R vector. So if this is a vector identity, so from here it is not an equation, it is a vector identity that both the left hand side and right hand side are equal. So it is an identity, not a result. So therefore it will be valid for any values of zeta. Since this is an identity, so it is valid for, so valid for any value of zeta. So it is valid for any value of zeta. Since it is an identity, so it will definitely value for any value of zeta. Therefore from I can also put my zeta to be 1. Therefore I can easily put zeta to be 1, and in this case my R vector, which is defined as A cross B cross C vector, this can be simply given as my results as A dot C B vector minus A dot B times C vector, which is the given vector triple product result. So this is how we can prove this particular relation. So it is proved. Okay, I hope this is clear to all of you. I hope this part is clear. Alright, is this part clear to you? Is this part clear to all of you? Is this part clear? So this is how we can prove the result for vector triple product. Alright, this result is very important and it is going to be very handy. Okay, so when we will solve the questions. Okay, so we'll definitely see questions on it. So the easiest way to remember this particular expression is something like, so please note there is an easy way to remember this expression, that is, so if I have my first vector as 1 and second vector and cross with third vector, if the bracket is placed over here, then the result is very simple. 1.3 times of 2 vector minus 1.2 times the third vector. Alright, this is how you can remember. Alright, so this is how you can remember this particular results. Now let's try to understand some more geometric implication of these types of vector triple product. So if we look carefully into this particular expression, this expression is giving you a result which is another linear combination of B and C vector. So if it is a linear combination of B and C vector, what we understand is that the vector triple product result actually yields a vector which is planar to this particular vector, which is planar to B and C vector. So whatever is placed inside the bracket, the result of the final vector will be planar or coplanar to that B and C vector, or that particular vector which is placed inside the bracket. Alright, I hope this is clear to all of you. And it is perpendicular to the A vector, right? So perpendicular to A vector and is coplanar to B and C vector. Okay, so this is the important relation that we need to understand, that why do we do a vector triple product. Alright, so this is a very simple product result which you need to keep in mind while we go on to solve questions. Okay, so let's try to solve and see some illustration to understand this particular topic in a much better detail. Let's say I give you a simple problem. So let us have a simple problem over here. So let us say that if my A cross B cross C vector is given as B cross C cross A vector. If my A cross B cross C vector is given as B cross C cross A vector, and the result of ABC are in the same plane, that means the scalar triple product result is equals to 0. If these results are given, then you have to find the result of this vector triple product. Okay, so to find this particular vector, so to find this particular relation. Please try to solve this problem. This is a very interesting problem and a bit tricky question. Okay, I won't say tricky that much, but it is basic conceptuals. Okay, that you need to actually understand in order to solve any types of problems. Alright, so please try to solve this problem and Let me know if you get any answers. Please let me know if you have any answers. This is a very interesting result and a very easy result as well. Okay, so please try to solve this problem. Please try to solve this problem. Please try to solve this problem. Alright, so let's try to see how we can solve this problem. So, if we look at the results which we have with us, it is saying that, so the problem says that the vector tailor product result of A cross B cross C, this result is equals to B vector cross C cross A. Okay, this is what is given. So if I expand the relation on both the side, this is very simple. It is A dot C times B vector minus B dot A times C vector, which will be equals to, again, it is going to be B dot A, that is I have defined far one dot product, and then times C vector minus of, then the closer ones, that is B dot C times my A vector. So this is my relation on both the sides. Now if these two vectors are equal, then their magnitude as well as the direction should be equal, right? So if I just try to simplify this expression further, and let me first of all combine the terms. So B dot C with C vector, with A vector. So I'm just combining the terms. So with A vector plus A dot C with B vector minus 2 times of A dot B minus 2 times of A dot B. So this and this will combine times of C vector is equals to 0 vector, right? So from here, now if this particular vector is equal to 0 vector, and we have seen by understanding of linear independence, so if these three vectors, also we have seen that these three vectors, A vector, B vector and C vector are coplanar, are coplanar, because we have this relation, that is the box product of A, B and C is equals to 0, which means that they are a coplanar vector. So if it is a coplanar vectors, then then this individual magnitude will be equal to 0, because there won't be a linear, this will be linearly independent, right? This will be linearly independent of these three vectors. Therefore, from here, if they are coplanar, oh, there just a mistake. If they're coplanar, then there will be linear dependence relation, right? So therefore, in this question, one modification has to be made, that it is not coplanar. It is not coplanar, and also linear independent result has to be followed. So what I can write over here is that these three vectors are non-coplanar. Okay, my bad. So these three vectors should be non-coplanar vectors. Okay, otherwise this linear independent result cannot be directly applied. So therefore, if they are non-coplanar, then what I can say, that is B dot C vector is equal to 0, and similarly A dot C vector is equal to 0, and also I have B dot C to be equal to 0, right? So if I have these following results as follows, that means A, B, C are all perpendicular to each other, and that can only happen if they are non-coplanar, right? Which is very obvious. So therefore, if I need to find out A dot B cross C, then the result will be directly coming out to be 0 vector. Okay, and this is a very interesting identity, that if my three vectors are perpendicular to each other, if A is perpendicular to B, similarly my B vector is perpendicular to C vector and C vector is perpendicular to A vector, then if I try to compute, so from here if I try to compute A cross B cross C, this result is going to be equal to a 0 vector. Okay, so this is a very interesting result which you can keep in mind. Alright, so please take this part in mind so that we can use this in the question as and when required, right? So with this particular understanding, let's now also try to go on define another system of vectors that is also called as a reciprocal system of vectors. So let's try to see what do we actually refer to by reciprocal system of vectors. Let us try to see what do we mean by reciprocal system of vectors. Okay, so let's try to understand what do we mean by reciprocal system of vectors. So let us say that I have three vectors which are given as A vector, C vector and B vector, C vector and A vector are the three vectors, be the three vectors okay. So if there are three vectors, then if I define another system of vectors such that it is a dash vector which is defined as B cross C divided by the box product of A B C, right? Similarly, if I define another vector B dash vector which is defined as C cross A vector divided by box of A B C, and another vector C dash vector which is defined as A cross B, divided by box of A vector, B vector and C vector. Then this A dash, B dash and C dash vector form the reciprocal system of vectors for the given set of vectors A, B and C. Okay, so this is another set of representing vectors which is quite useful in some times. So whenever we need to define another set of coordinate notation of vectors, so reciprocal system of vectors plays an important role. Alright, so these are the all important results that we need to understand, especially in order to deal with questions of chapters from vector algebra. I hope these results are clear. So with this, we are almost done with discussing the particular chapter. Also, one more interesting thing that we can also get out from or take away from this particular understanding of vector Taylor product is that the bisector of angle between two lines. This is a very interesting concept and I need to explain you this particular idea. Generally, when I ask you about the angle bisector, students definitely say that, so if I have two vectors, let us say A vector in over here and B vector somewhere over here. So if I ask you, so what is a vector which is bisecting this particular A vector and B vector? So if I ask you the vector which is bisecting it, generally students come up with the answer and says that if I take the sum of this vector by parallelogram law of vector addition, this particular vector is the bisector. That's what the student says, right? But that is a very important misunderstanding, that it is not the angle bisector. So A vector plus B vector is not the angle bisector. Why? I will explain. So it is not the angle bisector. Okay, it is only the angle bisector if I have my A vector and B vector to be a unit vector. Why? So if I try to understand this particular relation, that the bisector of two vectors, so or let us say this particular angle is theta, so bisector means this particular angle should be theta by 2, right? So this happens only when if I take A vector and B vector to be unit vector. So if I have to write my vector along the angle bisector, okay, if I need to represent a vector along the angle bisector line, then I can do it. So I can do that in saying that R vector is my angle bisector, that will be some lambda times of A vector upon magnitude of A vector plus or minus my B vector upon magnitude of B vector. Alright, so this will be the result. Okay, so please note that addition of two unit vector will help you to generate the angle bisector, okay, or the vector along the angle bisector. However, if you just directly add up the vectors, it won't give you the angle bisector. So it's a very important concept that we need to understand from the time now. Alright, so these are the important results that we need to think and understand, especially in this particular chapter is concerned. So in the upcoming chapters of 3D geometry, we are definitely going to use up all these particular concepts, and we're going to definitely use this particular concept to solve problems, right? So in the next lecture that we're going to take will be definitely going to be on the previous year question discussion. So we are going to discuss about the previous year questions on vector algebra, and we're going to wrap up this entire chapter of vector algebra. And with this, in the upcoming lectures, we will going to start with our new chapter that is going to be 3D geometry or three-dimensional geometry, where we're going to study about straight lines in 3D, planes in 3D, right? So those will be the basic understanding and the topic that we need to cover as far as the 3D geometry is concerned for the JEE syllabus, okay? So we are covering all this particular portion, especially taking in mind the JEE examination, okay? So whoever is going to prepare for the JEE examination and having their exam and currently in class 11 and class 12 and preparing for the exam in the upcoming year, then definitely this lecture is going to help you a lot, okay? So with this part, and also in the upcoming month of December, we're going to also launch live crash course on this particular channel itself. So in the month of December, we will be definitely see, because your first attempt for JEE Mains is going to be in January. So before that, I will definitely bring up a mock test. I will definitely bring up revision series, okay, where we're going to revise and prepare the chapters, okay? So that will be basically in form of a crash course where all the videos will be live over the YouTube. So please subscribe to the channel and also hit the bell icon so that whenever we are live, you get a direct notification. So with this, thank you, and I would like to conclude the session over here, and I wish you all the best.